Are quantum foam and virtual particles real, or merely figments of theoretical physics? This question has been at the heart of countless scientific debates. Let's delve deeper into this puzzle. The theory of quantum mechanics predicts a fascinating phenomenon known as quantum foam or space-time foam. This proposes that space-time at incredibly small scales seethes with activity, with particles of matter and antimatter ceaselessly popping in and out of existence. These fleeting subatomic objects are referred to as virtual particles. Another intriguing concept is the Kazmir Effect. Long thought to be strong evidence for the existence of virtual particles, the Kazmir Effect refers to the minute force observed between two uncharged metallic plates, placed very close together in a vacuum. However, the validation of these theories has been a subject of intense debate among scientists. Is this quantum conundrum a glimpse into the fundamental nature of the universe, or is it a mere mathematical abstraction? The Kazmir Effect, considered as strong evidence for virtual particles, has been questioned by several scientists. In 2005, Robert Jaffe of MIT argued that the Kazmir force is, in fact, the relativistic, retarded van der Waals force between the metal plates, not an effect of quantum fluctuations. This was echoed in 2017 by Hrvoje Nikolic, who provided a proof from the first principles of quantum electrodynamics, asserting that the Kazmir force does not originate from the vacuum energy of the electromagnetic field. He explained that the fundamental microscopic origin of the Kazmir force lies in the van der Waals forces. In a practical application of the theory, an inventor and a silicon etching business owner attempted to harness the Kazmir force to create a silicon perpetual motion machine. The idea was to use the Kazmir force to do work. However, the machine did not work as anticipated, casting further doubt on the validity of the Kazmir effect in relation to virtual particles. These instances of skepticism and failed experiments challenge the traditional interpretation of the Kazmir effect. They suggest that it may not be the definitive evidence for the existence of virtual particles, as it is often presented. These findings have cast doubt on the validity of the Kazmir effect as evidence for virtual particles. Similarly, the existence of quantum foam has been challenged by recent scientific findings. Let's delve into the year 2015, when a significant study shook the foundations of this concept. This research focused on photons, tiny particles of light, that had traveled for billions of years from a distant gamma ray burst to Earth. Now, according to the quantum foam theory, these photons, having different energies, should have arrived at different times due to the foamy, ever-fluctuating nature of space-time. However, much to the surprise of the scientific community, these photons arrived within a fraction of a second of each other. This simultaneous arrival indicated that all the photons had moved at the same speed, contradicting the concept of space-time foam. Adding to this, NASA also weighed in on the debate, looking for the telltale signs of quantum foam. But what they found, or rather didn't find, was just as telling. They stated, "The X-ray and gamma-ray data show that space-time is smoothed down to distances 1,000 times smaller than the nucleus of a hydrogen atom. This was far from the turbulent, foamy space-time that some quantum models predicted. These findings suggest that quantum foam, if it exists at all, has a much smaller size than previously expected." Given these challenges, the existence of quantum foam and virtual particles remains uncertain. We've journeyed through the intricate world of quantum physics, dissecting the controversial evidence for the Kazmir effect and quantum foam. We've seen how the Kazmir force, once considered strong evidence for virtual particles, is now explained by the more conventional van der Waals forces. We've delved into the search for quantum foam, a quest that has so far yielded no evidence of space-time's foamy structure down to thousand-fold smaller distances than the nucleus of a hydrogen atom. In conclusion, hard physical evidence for the existence of virtual particles and quantum foam turns out to be as elusive as hard evidence for Bigfoot and the Loch Ness Monster are, and leaves one rightly wondering if virtual particles and quantum foam are to be considered just as imaginary as those fictitious creatures are.